Sorry, I think you can start.
Yeah, I can start. Yeah, hello guys. In the last sessions, you guys have seen about regression models like linear regression, polynomial regression, I guess. Today we are going to see classification models like KNN. KNN stands for K nearest neighbors, and SVM. SVM stands for support vector machines and neighbors. And these are classifier models which are supervisor learning models, and we have the beginning we will give label data to them, and these things are mainly used for classification of data. We are going to start with KNN. KNN is very easy to implement, and uh, it is in the last. It is very easy model. So I will start with KNN and then I will go to SVM. KNN stands for K nearest neighbors, and it is a very easy to implement and simple model, and it can be used for both classification and regression, continuous value problems or regression problems. It is a supervised machine learning algorithm. As I said, these all three are supervised learning algorithms, and basically how it we will see how it works and how to K stands for the K nearest neighbors, like how many nearest neighbors we are considering during this model. We will see on the topic. We will see on those how to choose optimal K values and its implementation here. First, what is KNN? KNN basically predicts some data
Oh,
point
sorry, yeah.
based on, yeah. Hello.
Can you zoom in a little
Yeah.
bit? Yeah, just zoom in a little
Zoom
bit.
in. Yeah.
Yeah. Okay. Okay, this is fine.
This is fine. Okay. Yeah. Yeah. It is basically how it predicts something, which class a given a given input belongs to, like that. It basically predicts by seeing those neighbors. If there are two input, it is we need to predict what is the yellow point. Yellow point is belongs to a blue category or red category. We need to predict how our KNN will predict is, it will see its nearest neighbors. Nearest neighbors are its red and red and red. We can see it is, so it will predict like by taking the nearest neighbors, it will come to a conclusion. It belongs to a red label. Red label. If the blue label is here, it will predict the blue points are near, so it will predict the yellow point as blue. If the yellow point is here, if the yellow point is in the middle, it will take the nearest neighbors, and if it takes the k nearest neighbors, and it will predict based on how much. If there are five red points near and only two blue points near, it will predict it as a red point, like that. Basically how it is very simple. It is the basic overview of how it works. And it is when we are giving the input to the model, it just we need not to gain unlike linear regression, we need not to learn any weights, such things. It will just store the data. That's why it is called as instance based learning, and the model does not learn during the training period. Like training period is the giving the data points, label data points. During that period time, it won't learn anything. That is, it is called a lazy learning model. That is the why it is called lazy learning. And it does not depend on any mapping functions. Like in linear regression, it is called as y equal to mx plus c. Like that is the mapping, that is the function. But here it won't take any function like that. That is why it is called as non-parametric model, like that. In simple words, K take six for the K nearest neighbors. K, what we need to give the K value. K value we need to give it, feed into the model. So it looks for K nearest neighbors to it, and it will take how it will take. It basically takes the nearest neighbors by the distance, and it will predict the nearest the label the data. And even we can take if it is three, we can also give continuous values to it. But how it will work, like it will seek for k nearest neighbors and see those values. If the weight of three persons are like 50, 60 or 70, it will take the weight of three persons and makes an average of the weight, like that. It can also work on continuous values, but most probably we will use it as a classifier or label. it basically how it can take the k nearest neighbors by taking the Euclidean distance. But Euclidean distance is nothing but the distance formula we learned in the during high school, like that. This is the basic distance formula we learned during schools. This is the Euclidean distance, but it also can take a Manhattan distance or a Minkowski distance. But we not to do this, do mathematical in this. More, we will basically take Euclidean distance everywhere. And then we need to choose a optimal k value for that. We need to feed the k value to during for the in order to make the model predict take the k nearest neighbors. We need to give the k value. It won't take the k values. We need to give the take values, and with the k value it will predict the label. How we can give the k value? K value we can give by there is one formula called square root of n divided by 2, but this formula is roughly a formula, like we don't use many things, but it is a formula that n is the number of data points in the training period. But we don't use these things. Sometimes it may work. Basically, we'll plot k values versus the error. Error is the term here. Lower the error, better it is. So we will take the k value and plot a graph between k values and the error. We will repeat this process by taking different k values, and we will store the error. And by taking the by by taking the graph between error and k values, we can choose a optimal k value. Optimal k value is the value where the error is error on, and this is the test data and training error.
So
Where the
Surya,
test. Yeah.
there
Yeah,
is one
bro.
doubt on the chat. There's one doubt on the
Yeah,
chat.
yeah.
So Rutvik is asking whether Euclidean distance is the more accurate compared to other distances.
uh, like Euclidean distance is very useful in lower dimensions, but in a Manhattan distance and Minkowski distance, these are more accurate in higher dimensions. Like if the model depends on many features like those things, we will use Manhattan distance, and these are like we don't it's more towards mathematical rigorous proofs, or that to prove in higher dimensions Manhattan distance is clear. But most of the times, like 90 plus percentage of the times, we will use the Euclidean distance. It works very well for lower dimensions. Like if the input space, like number of futures, it depends. If it is lower, it is Euclid distance is good. I hope the basically, like I just want to show you these distance are there, but we will most of the times we will use Euclidean distance. I just wanted you guys to show you these are also there. That is the thing I want to show you. Yeah, I
Okay,
hope.
now move on.
And yeah, here we will choose the optimal k value by taking the error values and the k values, plotting a graph between error and k. The optimal k value is the k value which gives the lowest error on the test data. So we will choose like that. And after that, when the optimal values arises, we will use the we use the k value and deploy our model in the real world or something like that. And conclusion of this is KNN is a powerful algorithm, but the problem arises is like if we are giving so many points, if the data set is very huge, KNN will take so much time to compute, because you need to compute because it need to compute all the distance, so it can take the minimum distance and those things. So when the data set is very large, KNN will take so much time. That is the main problem in KNN. And it's in some environments it is impractical. Like if the data points are more than 5 lakh data points are there, it is obviously it will take much more time than any other model. So it will be impractical many practical uses. And it is best thing is if the data points are simple, and if they are clustered together, it is very easy to implement, and it is faster in lower data points. If the data points are very lower, it can be faster and accurate. But main problem goes to in most of the practical applications we will deal with many data points like 5 lakh or 5 million data points like that, in millions of data points. So that in those practical cases it will be not feasible as other models. That is the thing. And Kane can be used to like if you are seeing some new movies, if you are browsing in Netflix or YouTube, if you how to give you a relevant data, relevant movie, or relevant, if you are watching horror films, you can get recommendations as horror films. And if you are watching action films of Tom Cruise or something, you can get recommendations of those heroes done by those movies done by those heroes, like those movie categories, like those things. It will give you recommendations, and this kind of things can done with KNN, like those things. It will basically to give you a relevant content like that. And here we are going to implement KNN iris dataset, which I have shared to in the group. Iris datasets contains sepal length and sepal width of the flowers, and the petal length and petal width of the flowers, and the species of the flowers are iris setosa and iris veris. 1 minute, I will show you. Yeah, these are the three flowers we are going to take. Iris setosa, Iris versicolor, and Iris virginica. These flowers are we are these the data set is about these flowers. We need to by using these petal length and sepal length and petal width and sepal width. We need to classify uh, whether whether the whether it is a which flower like that. These are the features we are going to use: sepal length, and these are four features. So it is a four-dimensional data. Dimension of the data is the dimension of number of features available in the data. Okay, we are first we are going to take species. First, we are going to read the CSV file, and we will print the head of the CSV file to get an idea of what these are, what these things are there, and those things. And we will take only the feature data. Features means up to these four, 1, 2, 3, 4. These things to get the value of only these four values. We will take these things to get it. We won't take the fifth thing. Fifth thing we will take as a species values. Species is the target value, and we will take the these four things as the feature value. We will feed into the, this is the x values and this is the y values in common term. And we will shuffle those data to get more accurate models using the shuffle function. And we need to import this function. In the top I have imported those functions, and in the x train and this is a train test split. This is the function which is available in sklearn. The basically what it does is, we will give this feature data here and the species target data here and the test size. Test size is a 0.2. 0.2 means it will separate 80% of the data into the train data and will give 20% of the data into the X test data. X test data is used to verify our model. We will use this function to get our X train and X test data. This is a function which is available in sklearn library. I have imported this function in the top. And the standard scalar, this is a function we use to standardize the data. Standardize the data means we will if this is the sepal length, we will calculate the mean of the data and also the standard deviation of the data. And then what we will do is, we will for each of the value we will minus the mean of the data and divide it by standard deviation. Everyone clear about this? We will minus the mean of the data with every values of this and divide it by the standard deviation. Everyone clear about this, right? And why we are, I hope everyone is clear. And why we are doing this, to make the mean of the whole columns equal to 0 and the standard deviation equal to 1. That is the main. That's why we are doing the standard scalar function over that x train and x test data. And we are using here only fit transform, but here we are using only transform. What fit transform do is, it will take the extrain data and calculate the mean and standard deviation of these data and minus the same mean and divided by standard deviation. But the transform, what it will do is, it will take the mean and standard deviation of the training data, not the test data, and it will subtract the mean with it, and the standard divided by the standard deviation with the values in the columns of the x test data. Because why we are doing that is, we need to we are x test data is only 0.20% of the data. 80% is extrain data. We need to make our model perform very well in unknown data. If the extrain data is correct and everything is clear, every value is correct, everything follows a distribution, like its mean and its standard deviation should be almost same as X test data. That's the main thing we are doing here. That's why we are not using the fit here. Only transform we are using. And this is the thing we need to use. Like there is some other things called min max scalar, like those things. We need to use those things in some other cases. After that, we will import. I think everyone is clear about this point. If everyone has a doubt, anyone has a doubt, you can ask. O- Okay, everyone is clear about this point, I guess.
No, Shivasudha.
And yeah,
They're asking you to repeat about fit transform.
fit. Yeah, okay. What we are going to do is, if this is let's say there are only five values, we will take the mean of those values, and after taking the mean of those values, we will subtract the same mean with these values, with the all five data. You are clear, right? And we will, and after we will take the mean and standard deviation of these values, and we will subtract the mean with every values here. And after subtracting the mean, we will divide the data with the standard deviation. That is the standard scalar function. That's what standard these things will do. We are using fit here because we will take the mean of these 4 5 values, and we will subtract these values and divide it by the standard deviation. And we are using only transform here because we won't take the mean of the futures in the x test data, but we will use the mean which is taken in the x train data, and use the mean to subtract here, and use the standard deviation which we took in the x train data in the x test data also. We won't take the new mean and the new standard deviation. We will use the data mean and standard deviation which we calculated using the x train data itself in the x text data also. We won't calculate new mean and new standard deviation here. We will take the old mean and the old standard deviation. That is the main thing difference between fit and fit transform and transform. Can you get me, or should I repeat? Do you have any doubt?
Yeah, you can go on.
Okay, yeah, I hope this is clear. Okay, then here we are importing k neighbors classifier. This is the knn, which is the scalar function, and I'm just using here to like the square root of n divided by 2. That thing, we have 120 data points for the extrain data here. That's why I'm using 120 into power 0.5 into 2 to give you some list of range of values like that. Basically, I'm generating the list of k values here to plot this data k values versus the accuracy. Here it is accuracy. Okay, I will create the classifier KNN using the scalar function which I imported here. Using n neighbors, I will use this I value which is generated by the range function. Basically, here I'm starting from 3 and I am going from some values. You can see here I'm going up to 60, 65 something, 65k values. And I am repeating, and I am creating a nearest neighbor classifier function, that model, and giving input as the k neighbors as the input starting from 3, and I am
Hello.
fitting the function. Hello, yeah.
Yes, that k value is
Yeah, yeah.
square root of 120 by 2, right?
No, like the thing is, like I just wanted to show you, like some people say like it is square root of n, and some people say like square root of n divided by 2. The best thing you can do is like choose like k values from 3 to 100, 3 to 1000, like according to your model, and iterate through them and generate a graph like that and choose optimal k value. This I just wanted to show. It is just a stock overflow question, and we need not to rely on this. I just wanted to show you the things just exist. Just wanted to show you. Yeah, can you? I hope your doubt is clear. Like the best practice is to iterate through a set of k values, and then I iterate and then generate a list and iterate through this and get values of get a set of k values and plot it versus accuracy or loss. That is the best thing you can get the k value. I just wanted to show you those things exist. Okay, I think the doubt is clear. Yeah, yeah. Yeah, okay. I think the doubt is clear. Yeah, we are fitting the function with the X train and the Y train data. I think they have also like a linear regression team also have gone through these things. Basically, it will train our KNN model, and we are predicting the Y prediction value by giving our X test data, and using the Y prediction value, we are getting the accuracy score. Accuracy score is a function which is also available in sklearn. I have imported this function in the top. Using the accuracy score function, if you feed in the y test data and the y predicted data, um, y test data is the real data. It will give the accuracy. Accuracy is the number of points mm, we have predicted correctly divided by the total number of points. Like that. After getting the accuracy, I'm just iterating to all like for n neighbors, and I'm appending these functions here and appending the accuracy list. This is a list of accuracies. Appending the accuracies to it using the append function in Python, and I will get a list of data, and I'm just plotting the list of data and versus its accuracy. Here we are using accuracy, so higher the accuracy, better the k value. So by using the pld.plot function, I'm plotting the accuracy, and using r means red color label I'm giving and I'm showing the accuracy. Here greater the accuracy, greater the k value, and I'm seeing, you can see here like first some of the up to some point like 30k values, I'm getting accuracy of 1, which is the highest accuracy, which means 100% I'm predicting correct, because it is the why I'm getting one accuracy is iris dataset is a very good dataset, and it is not a challenging dataset, it is a very ideal dataset. So I'm getting accuracy of 1. But you can see, even though it is a very good dataset, if as soon as I increasing the k values up to 65, I can see accuracy is dropping up to 86%. That's the thing. Like we need to iterate through the many k values. Just don't use those functions. Square root of n divided by 2. Don't use those things. Just iterate through many k values and get an accuracy or which is which gives the higher accuracy, or if you are using loss, which gives the lowest loss, is the best k value. If you are using accuracy, something like that, which gives the best accuracy, is the highest good k value. Here up to 30, it is giving accuracy on something 30 like that, 30 or 26, something like that.
Shiv Surya, there are two doubts. So
Yeah.
Ishan has a doubt. Go ahead, Ishan. Ishan, I think you can unmute and speak if you want. Okay, so I think they didn't have any. So, okay, so Rutvik is asking, can you explain the k underscore val is int 120 power 0.5 into 2? So, where had you written
Oh,
that?
okay. This is causing so much problem. I guess I will get rid of this. I am just used that to like Um, yeah, I'm just because it has 120 data points and it has 0.05. 0.5 is the power square root of 2. I'm using power 0.5 and I'm using just to get a value of 60 up to 60 like those things. K is equal to I'm generating up to 3 times of K values. I think that's why I'm using here. Like it may give up to 20 and into 3 it will give up to 63 like that. I just wanted to get more K values. I'm just using some random number. Like I can also use 4 or something. I'm just wanted to show you like with the high range of K values how the accuracy drops like that. I will when I am uploading the character notebook, I will just get rid of this and I will do something like you can put 100 here or 10 here and you can experiment with any number of K values, 100 K values, 1000 K values, anything. I just wanted to like show you like number of K values. That's the thing. Yeah, I hope this clears.
Yeah, I think if anyone else also has any doubts, you can feel free to unmute and ask anytime.
Yeah. Okay, I hope no doubt is there. If anyone has a doubt, feel free to unmute and ask. I'll just give you a recap. KNN is basically depends on K nearest neighbors. We need to give the K value to it. It is an supervised machine learning algorithm and it is non-parametric because it don't depends on any function. It will choose the nearest neighbors by taking its Euclidean distance and there are some distance also there and we are not really going to use these things. I just wanted to show you and these k values we will choose the best k value by plotting the graph between k error and k values or accuracy or k values. Higher the accuracy, higher it is better. Lower the error, it is the better k value. And after iterating like this, we will choose the optimal k value and we will deploy our model in the real world or real time with the k value, with the k value which we have found. The conclusion is KNN's main disadvantage is it is with higher data set, it will take so much time. That is the main disadvantage of KNN. If you have any doubt, feel free to ask. It is very simple model KNN. Anyone has a doubt? Okay, I think I will move to SVM. Next, we are going to see support vector machines. And the thing is, SVM is a very powerful tool in machine learning, and it is it cost wise time also it also takes so much time, but it is more powerful than KNN and other models. Neighbours KNN, it is a very powerful tool, SVM, and there is quite a bit of math also behind SVM. We will go through it. We will get an intuition about this, no problem. Here you can see I have imported pandas, SPD, numpy, NP, and this shuffle function, and the train test split which I used in the DOM, and standard scalar function. And there is one another thing called min max scalar. Go through. You can after the session you can go to the website and see those things. This is the support vector in logistic regression. Sorry, Gaussian we have imported and the map model. This is the data set we are using. Iris data set. I have gone through it. And these are the data sets. Like we can get the insights from the data sets by using. This is the head of the data set. This is the tail of the data set, and we can get some insights using the data.info function. I hope these things are covered during the pandas session. We are just extracting. Like we will go into it. We will just see like how data is how data is given as to. I think someone need to unmute. Someone need to. Okay. This is just to show how the data is scattered over the thing. It is about the setosa and it is very similar. You can see how the data is cleanly separated among themselves. That's why KNN is giving so much high accuracy there. We will also use this data in the SVM, and we will also get good accuracy in SVM also. Okay. And what is SVM? SVM is nothing but how SVM works is it will make an hyperplane between these data. It will make an hyperplane between these data. In 2 dimensional it is just a line. In 3 dimensional it is a plane, and in 4 dimensional it is just a hyperplane between these data, and it will, if it is below this, it will separate this as something else, so it will give some label to it. If it is above the plane, it will give some label to it. That is the main concept behind SVM. The only thing we need to find here is SVM with the maximum margin. uh, that is the main thing behind SVM. And in a data set, we will there may be like many hyperplanes possible, but how we will choose the optimal hyperplane? How we will choose the how that is this hyperplane also separates the data, this also separates the data, but this also separates the data. But we will choose the optimal hyperplane by taking the maximum margin. Maximum margin is the distance between the this hyperplane and this distance between the nearest point to the hyperplane of the two classes. Which hyperplane gives the maximum length. This margin length will be our hyperplane. That is the hyperplane we are looking for in SVM. In SVM we can everyone knows, like we can describe a plane equation as w dot x plus b equal to 0. W is the weight and x is the dimension, or like x1, x2, x3 like that, and b is the bias or the interest. Y, it is just like the formula y equal to mx plus c, or ax plus by plus c equal to 0. A and b are the weights there, and x and y are the features there, and c is the bias thing. We will this is the basic equation of the plane. That is the wx plus p equal to 0 is the hyperplane we are looking for with the maximum margin in SVM. And in SVM, in order to separate these things, we will give label to this data. We will give label not as 1 or 1 and 0. We will give them a label as -1 and +1. Here we are giving label as +1 to blue colors and -1 to orange colored labels. And we need to separate, give labels like this. That has a reason. We will look into it. Any doubts here up to this? Everyone can follow it. Yeah, I think there are no doubts. And then first we will get our data, and we will give labels like +1 and -1 to corresponding data. We need to give +1. And how we will separate this data, like if this is the hyperplane, if we pass a point here to the equation of this hyperplane, it will give some value like greater than 1. And if you pass which is above hyperplane, it will give plus or minus value. If this gives minus value, this will give plus value. But if it gives minus value, it will give plus value. What I'm saying is, if this is the equation of the hyperplane, if you pass a point which lies in the hyperplane, it will give 0. Everyone is okay with clear with that, right? If you pass a point which lies in the hyperplane itself, it will give 0. But if you pass a point which does not lies in the hyperplane, it need to give some plus or minus value, right? If it is down in the hyperplane, not necessarily it need to give minus or plus, but if it is down in the hyperplane, if it gives minus. If some point which is above the hyperplane, if you pass the point into the equation of the hyperplane, it will give minus. If it gives plus, it will give minus. It will be opposite sign. Those values will be. That is the main concept we need to clear here. If you pass a point here which lies in the hyperplane, it will give 0. If you pass a point which does not lies in the hyperplane, it will give either minus 1 or not necessarily 1. It will give a negative value or a positive value. That is the main thing we need to clear here. Everyone is okay with this, right? Everyone got it right. Yeah, everything is clear, I guess. And after that, if let's say it is giving minus value, this orange color values are giving when we are passing the points, the orange color value is giving minus value, but the blue color ones are giving plus value when we are passing the values to the hyperplane. If it is giving a minus one value, sorry, minus value and negative values, these things are separated by some distance, right? These things are separated by distance. It should give some, let's say, it can be any, it need not to necessarily be one, but it can be any values. But if it is some plus, or if it is plus one here, it should be minus one. If it is plus two, it should be minus two here. If it is plus three, it should be minus three here. These should be same values, but it can, if one is positive, one should be negative of the same values. That is the main condition we are looking for here to create an hyperplane like this. This is the condition we are giving. This is the condition we are getting for this hyperplane. If we pass this value, we are getting greater than one. Let's say let's assume one here, and let's assume when we are passing this orange here, it is giving less than minus one. When we are passing the blue values, it is giving greater than one. We are passing this data points to the equation of the hyperplane. The here hyperplane is here, and we have given the data as we have assigned blue color equal to plus one and orange color equal to minus one, right? These are two values, but if you as it is giving a positive value, if you it is giving greater than or equal to positive one value. If you multiply plus one with the positive value, it will give greater than positive one value, right? But if it is as it is a minus one value, the orange color we have labeled it as a minus one. It is and when we are passing the data points of the orange point to the hyperplane, it is giving less than minus one value. After multiplying the yi value for orange is minus one with the minus, it is giving less than minus one values. After include multiplying both minus, it will give, then it will become positive and it will starting to give plus greater than one values, right? That is the main thing. Like after multiplying these labels with the data, the point plus or minus one values, we are getting for both, we are getting plus one values, greater than plus one values, right? That is the constraint to find the correct point. If some data which is some point which is passed into the equation multiplied with this label gives greater than some one or two something, some values we can any values is okay, it will give the positive value. That is the constraint we are looking for. Everyone is okay with that? Everyone is getting it? If you have any doubt, just ask. Everything is okay? I hope everything is okay. Yeah, here like we can use any c values. So like that, give it as a small c values. Like if you use some big values, it will take so much time to learn. Basically, you can give one. One is the main thing. You can one, but you can, if you give two here, you need to give minus two here. That's the thing. By taking the multiplying this thing, we will get always greater than plus one value. That is the main thing, the main constraint here to make a point correctly classified or not. To know whether we have classified a point correctly or not, it should give greater than plus one. Here, everything is okay. Everyone is okay with that, right? I hope it's clear. Okay, let's move on to the loss function. How, like, loss function is the main thing which we use it to update our variables. And we are using loss function. The loss function we are going to use here is lambda times half into modulus of w. W is the weight square, weight vector square, and max of 0 or 1 minus ya into w of xi plus b. This is the term we are going to use here. And just look at the term. Just look at the second term. Just look at the max of 0 or 1. Just take look at this term. And why we are taking as max of 0 of 1 minus ya and w of I plus b. When we are when we are correctly classifying the data, there is a one constraint, right? Ya into xi plus b is always greater than 1, right? When we are correctly classifying a data, there is a one constraint. When we are calculating a max, this will be greater than 1, but as we are adding minus, this will be negative value. This term will gets negative value when we are correctly classifying the data points. So it will become a negative value and 0 become the positive value. And as long as our SVM is correctly classifying the data points, we need not to include the loss rate. There need not to be no loss. That's why we are giving 0 loss there. But if it is wrongly classifying the data, it here with this term the minus 1 get multiplied, so it will be less than minus 1. Here also it will get plus 1 get multiplied, so it becomes less than minus 1, right? So when we are when our model is not correctly classifying the data, it will give minus values, so minus greater less than minus 1 values. So it will become more, and we will calculate the loss function for that. If only one and only if it is wrongly classifying the data, it will become minus value, and minus into minus it will become plus, and it will we need to calculate the loss function for that, for the misclassified data. Only if the data is correctly classified, it the whole term becomes negative value, and since we are using the max function here, we will get the 0 as the result. That will be no loss. But if our model is wrongly calculating these things, this whole term become some positive values, so we will get the loss function. We will get the loss there. That is the main thing yeah, about this thing, the max function. And everything is getting clear, right? Everyone is clear about this, right? If you have any doubt, you can ask. Okay, everyone is clear about this, I guess. That is the main intuition behind this using this loss function. And the loss function, why we are including the modulus of weight square term. This term we are including this to increase the marginal distance. Marginal distance is we need to minimize w here, the weight here, because we in our textbook we can see a formula like the distance between a point and the line is ax plus b y plus c divided by square root of a square plus b square, right? Like those formula. The distance between a point and the plane is inversely proportional to its weight. We can prove it mathematically here. If you want to look into it, you can look into it. It is simple point. The result is the important here. The the distance, marginal distance between point and the plane is inversely proportional to its weight. So we need to increase our we need to increase our margin, so we need to decrease our modulus of the weight. So we are including this in the loss function. We will decrease we will work on to decrease the loss function. As we decrease the loss function, this modulus square term will also get decreased, and this also will decrease. Then we will get a good hyperplane with a good margin. That is the main thing why we are using a modulus of w square, weight square here. Everything is clear, I guess. If you have any doubt, you can ask. The marginal distance is inversely proportional to modulus of vector w. That's why we are including it in the loss function. Our overall aim is to decrease the loss function, so we can get a correct classification terms, and we can get a better classification. We will work on decreasing the loss function. That is the main training of model. Okay, we got the loss functions, and by using the loss function, we need to update our model. For updating our model in the linear regression also, you have seen like we will differentiate the loss function with respect to the variable we need to update, and we will use the negative of the we will add the model with the negative of the differentiation, right? In the linear regression also, you have seen you have see like they are differentiating the loss function with respect to m or some the weight, right? That is the same thing we are going to use here. We will differentiate the model, our model, with respect to w is the vector, and also with respect to b is the bias. Yeah, this b thing. We will also we will differentiate the model with respect to w and with respect to b. These two things are the things which is going to these two are the things which is going to influence our define our hyperplane. We need to get an optimal value of w and b. That's why we are differentiating the loss function with respect to w and b, and updating our weights with respect to w and b. After differentiating the loss function for misclassified for a misclassified object, like if I assume correctly classifies everything, we need to do one thing we need to do is only to increase our marginal distance. If our assume is wrongly classifies some things, we need to increase our accuracy also, as well as our margin. We need to correctly classify those things. So we are getting this loss function from this max of 0 and 1 or 1 minus y into w dot xi plus b, and we are also getting this lambda into 1/2 into modulus of w square. These are the loss functions we are getting. If our model is not classifying correctly, we will get two loss terms, and if our model is correctly classifying, this will be 0. As long as we model is correctly classifying, we need to penalize our model. There is no loss there, so it will be 0 here, and we will calculate only. We need our only focus is to increase our marginal distance. We will use this. And taking the partial derivatives with respect to the two steps, we are getting like lambda into wk. You can take the 2 will go here, it will get cancelled, and lambda w. And with respect to b, there is no difference of b term here, so it will become just 0. And here like same thing, lambda will go here, 2 will go here, and lambda into wk will come here, minus this term will go here when differentiating with respect to wk, and the b term will go 0, and the only term which is dependent on w dot xi ya is there, and this term will get it cancelled, and it will get minus 1 ya into xi. We will get like that. And with respect to b, differentiating with respect to b, this term will become 0, and this also will become 0. These term only these term will become these terms will become 0, and only this term will be there, and we need to multiply this term with this term, and it will get 1, and we will get only this thing. This thing this will get 0, and this will become 1, and 1 into ya minus ya, we will get minus ya. That is the main thing. While we are differentiating, we will get to increase our weight. After differentiating those things, we need to update our weight rate. This is our learning rate. Learning rate also should have been discussed in the linear regression. Also, we will give us as 0.01 something like that, or 0.001 like that. And the lambda times w is the w. This is the lambda, and c. We also use a variable parameter called c. C is the variable. Like how hard it is used to define how we will penalize it when there is some misclassification is there, whether it is used to tell us whether the margin is hard margin or soft margin. If the c value is very higher, it will call as hard margin, and it won't classify any data like that. It will always classify, it will draw a margin like that. If the c is higher, it won't allow any outliers, and it will classify, it will make a margin like that. So every data point blue points are inside the margin, and every others are like this. every other data points like this. But if the C is less, it focus more on margin, increasing the marginal distance. If the C is less, it is called a soft margin, and it will draw a line like this. Instead of drawing like line like this, if the C is less, it will draw a line like this, so it has a maximum margin instead of having all the data points in one side. It focuses on making a maximum margin.
So,
That
yeah,
is the
maybe
yeah
could you zoom
yeah
out? I
bro.
think it is very slightly zoom out. The image is not properly visible.
Yeah,
Yeah, okay. Maybe repeat what you said again.
yeah bro. We are using a C term here, and the C term is used to tell us whether the margin we are drawing, the hyperplane we are drawing is soft. Hard or soft in the sense, if the C is higher, it won't allow any outliers. It will make a margin such that every data points, or it is correctly classifying. It focuses more on correctly classifying all the data points instead of making a good margin. Here you can see the margin is very less. If the C is higher, it focuses main on classifying the data points than on margin. If the C is very low, it will basically tries to make a more margin instead of making a good classification. It will make a it will draw a line such that the margin is very high like this. It will draw a line like this instead of drawing a line like that and making a more margin. Even though it is there, it won't care. Like it focuses more on making a more margin. But see, if here the C is higher, but so it is making a small, it is focusing on small margin, but making a good classification like that. We need to choose a optimal C value according to our data set to get a good prediction like that. It is a bad prediction. We can see like it is a clearly an outlier, but it has drawn a margin like giving a high C. But we the margin should be like that, so it will work very well on the unknown data. It overfits this. Here the margin is very low, but if the C is lower, the margin will be very high, and it focuses more on margin. If C is high, a margin will be very low. It focuses on classifying the data points more accurately. That is the main thing I want to clear. Do you have any doubt? If you have any doubt, feel free to ask.
So I think one thing I'll just mention. So all these different methods are there, right? These are all independent methods. So you don't need to know KNNs to learn SVMs, or you don't need to learn
Yeah.
SVMs to know naive Bayes or polynomial regression or whatever, right? These are just different methods that people use to train their models. I mean, like choose their models and also get different results.
Yeah. Anybody have some doubt?
Maybe let's do one thing. We'll take a short 5 minutes break and then we'll resume back again around three
Yeah.
five. Is that fine? Yeah, I think 3 5 is fine.
Yeah.
Thanks, Surya.
Yeah. 3. Yeah. 3 5. 3 5 3 3 like. Yeah. 3 5 is fine. Let's have a short.
Yeah, I think so, sir. You can start again.
Yeah, I'm going to just give a recap for this what I have covered here. SVM is SVM is all about dividing the data points by a hyperplane. Hyperplane is a plane which divides the data point or some any plane in general, and it divides the data points by choosing a hyperplane which has the maximum margin between the data points. It is in 2D, in 3D, in 4D we cannot visualize, and we will give the mark how we will how we will divide the points by giving the points a label of plus and minus one, and these are the conditions which will be satisfied by correct classifications. Which the opposite of the thing is satisfied by if it is a wrong classification, it will be less than minus one if it is wrong. If it is correct, it will greater than one. And we will define a loss function for that. This term is used to get the we have maximum margin, and this term is used to classify the points correctly. We will introduce another parameter called C, which is used to define whether the margin is hard margin or soft margin. Hot margin is the thing which classifies the. It main thing is it need to classify all the data points in. It will focus more on classifying the data points correctly than the margin. But if it is a soft margin, it will even if some misclassifications happen, it will focus more on margin. It will draw a line like this, and it will focus more on having a more margin than classifying the data correctly. We need to choose a optimal C value while we are deploying our model. That is the main thing we are. So far I have covered here. Like I have in the last half an hour, I went into some detailed mathematics. After that, these are the main intuition behind this. And here, as of now, we have seen all the models are linearly classifiable. What if the model is not linear? We cannot classify the model simply by drawing a line. What we can do for that? For that, we can use a thing in SVM called kernel method or kernel trick. We will tell if the models are like this and it is not linearly classifiable, we will make them into a future. In the input space, it is a two dimensional input space. We will transform them into a future space which has a three dimensional. So the model become a linearly classifiable in the hyperplane in the future space. In the 2D we cannot classify the model with a simple hyperplane. But in the 3D, we can see the blue points has taken a upper higher z value, but the red points have taken lower z value. So we can easily classify them and with the hyperplane in the 3D space. That is the main thing we can behind the kernel method. And when you are transforming, there are many kernel methods here in SVM, like RBF kernel, polynomial kernel, like that. Each kernel has its different features. And what is the RBF kernel is if the data point is like this, if it is like a circle, it will mark it into a feature space which is depends on the radius with distance between the 2 points. Is the distance between the let's say if distance between origin and these points are very low, so it will mark them into a 3D space where the z value is inversely proportional to the distance in the 2D space. It you can see the red points are marked in higher has a more greater z value, but the blue values have lesser z values because yeah, when while transforming to 2D to 3D, it will give their points and z value which is inversely proportional to the distance. So let's say it is origin and it has these thing red points are in very closer to origin, so it has taken higher z value in the 3D space, and blue values are closer to far away from origin, so they are taken very low z value because they are inversely proportional to or this is one type of transformation. Transformation is nothing but passing a point into it and marking them into some other dimension like that. It is a transformation in 1D. It is data is like this. For zero, there is cube is there, and For 2 the cube is there, and in 1 the round is there, and like that. If you mark if you make a transformation like x into mod 2, which are following a multiple of 2 will get a 0 value here, which are getting a multiple of 2n plus 1, like odd values will get a 1 here. So we can easily classify them in the 2D space, which are not separable in the 1D space. We are just marking them into a higher dimension like 2D, then we are easily classifying them with a line. That is the main thing with kernel trick. Which are not separable, easily separable in the input space. You will just transform them into a feature space which is separable, which makes them linearly separable. That is the main intuition behind the kernel trick. And the main kernel we are basically uses RBF kernel. The formula for RBF kernel is like this. Here we need to take main look. We need to take a careful, carefully look into the gamma thing. Gamma value, like if you have more gamma value, what happens is it will make it more dependence on the distance. If it has very less gamma value, it will become less dependence on the distance, like how I'm saying that. You can see the gamma is very low, but you can see something or even misclassified here, but it has a very large distance and it is classified like this. But if the gamma, as soon as the gamma is increasing, you can see if gamma is very high, it is classifying the all training data correctly. It is basically overfitting this. You can see it has made an input, it has classified these points by giving a very small margin. Like it basically takes it classifies with small margin like those things, so it will overfits the thing as gamma increases. If the gamma is reduces, it makes more circle with more thing with a higher radius like that. But if as gamma is getting closer and slower, closer higher and higher values, it is basically overfitting everything. You can see here, this is the RBF is the thing we will use in many cases. For kernels, we will basically use RBF for many times. And there is another called polynomial kernel, which has a formula like this. You can see, and while we are using kernel, we also use the C values. The C value which we have defined here, the margin. We need to while using the kernel method, we also give we will also pass the C values according to the situation and accuracy you want. We will tune the gamma and C values according to it. The main thing we need to note it, as the gamma value reduces, as the gamma value is very low, it will tend to underfit, and if the gamma value is above, so like if it is higher, it will tend to overfit. The gamma values like OKs, it will tend to with perform well in real world like those situations. It will can give an higher accuracy in real world. That is the main thing we need to talk about here, and we also need to perfectly tune the C value also. And this is the formula for polynomial kernel, and we can also use this kernel. We need to give the d value for using polynomial kernel, and we can using grid search like those things. Grid search is it will put random gamma values, and it will see how it behaves with the input data, how the error changes, and it will choose it will automatically give you a good gamma value d value upon and the accuracy. Grid search is basically those things. At here we are going to implement sklearn SVM using sklearn library. Has yeah. Yeah. Okay. Do you have any doubt? Anyone has any doubt on the kernel method?
Maybe you can just go over it once again, right? Maybe don't go to the map, just go over it what happens, and then can go
Yeah.
up.
Okay. Okay. I will start now. In kernel method, basically what we will do is we will take a input in the input space, which is not linearly separable in the input space, and we'll map them in a higher dimension, so it become easily separable. This is an example, like you can see here, it is an example. This is clearly not linearly separable in the input space, But if you map like a red point, if you map the z value of those points will take it will be inversely proportional to the distance. If we map with a function like that, the z values become higher for the red points, and the z values become lower for these blue points. So we can easily separate these things. That is the main thing with the kernel. Kernel that is the main thing what we are going to do with the kernel tree. And we can say see a one-dimensional thing which is not linearly separable in one-dimensional. But if we map them into a two-dimension like this, such that modulus of 2 by mapping function of modulus of 2, which are having a 0, 2, or 4 even values would get 0 in the two-dimensional space, which are having a 1, 3 like odd numbers, which will map it to a 1 in two-dimensional space. So we can easily separate these things. Their y values become 0 in which are taken even values here have y value equal to 0 in the two-dimensional space, which has a y value which has odd numbers. Taking odd numbers in this linear space will take y value equal to 1 in the two-dimensional space. So we can easily separate them with the linear line. That is the main thing about kernel tree. We will we will we will map them in a higher dimension, and we will make a hyperplane which is we can separate them with a hyperplane in the higher dimension. Here in real situations, we will use a RBF kernel, which is called as radial basis function, which is depends on the distance between 2 points. You can see the modulus of the distance between 2 points, two vectors. And the main thing we need to see here is the gamma value. As the gamma value is very low, it will tend to underfit. If the gamma value is very high, it will tend to overfit and make boundaries like this. Here the boundaries are boundaries are more constrained, like very less, and here boundaries are free, like very free in underfitting. The boundaries are appreciable, like it can give good enough to give good predictions in optimal gamma values. We need not to give higher gamma values or lower gamma values. We need to search for good gamma values, and then our model can get good prediction in RBF kernel. There is another kernel called polynomial kernel, which is basically this is also a formula. We need to give the d value. We can by using this we can also get we can also make a map into a higher dimension like those things. But most of the cases we will use RBF kernel. It can work well on many data sets like those things. I think everything is clear, I guess. One thing we need to see is as gamma value is very low, it will underfit. As the gamma value is higher, it will tend to overfit. And we also need to consider the C value, which we discussed in the top. Yeah, I think if anyone has a doubt, you can ask. Okay, I think I will move on to the implementation part of the SVM using sklearn. As I said before, I'm using the data which I already extracted in the top. I'm going to use only two features. In the top itself, I have extracted the data. I'm going to use only these two features values, sepal length and petal length. So I can show you the line separating these two classes of data. Only two classes of species, Iris setosa and Iris verisca, and so I can show you a good separation plane, how it separates those points. It is better to visualize. So I'm using only two features here. And I'm shuffling the data using the shuffle function, and I'm putting random state, so I will get a same result all the time. And I'm making a train data and test data and y train and y test data using the train test split function, which is available in sklearn. And I'm just printing the shape, so I can see like whether I have created the correct shape of the data, whether everything is going correctly. And I'm importing the sklearn SVC. SVC is the for SVM for your implementing SVM in a sklearn library, and I'm also importing accuracy score here to get the accuracy of the thing. As you can see, like I have created my SVC model using the linear kernel because these data points are linearly separable. You can see. So I'm using linear kernel, and I'm using the fit function there. Fit function. By using the fit function, I'm training the model, and I'm predicting the model by using the test function, and I'm printing the accuracy score here. And we are getting one accuracy. No wonder, like easily they are easily separable. And then I'm printing the coefficients of there are only two test fuses are there, right? So the coefficient, the model it will make is ax plus by plus c equal to 0. That is the model. That is the line we are getting here. It will make so we are getting the two coefficients and the intercept also I'm getting. I'm changing the intercept into y into a mx plus c format, and I'm here I am just drawing the line. I'm just scatter plotting these points, and I'm drawing the line here by using the matplotlib. I think there was one session in matplotlib, and you have covered those things. Yeah, that is the thing I'm doing here. And here I have implemented my custom SVM to show you a thing like how it makes a model prediction. Like you can see at first it is making a line like this, and after training it is just making this upper, and after like this it is making a good prediction. Like it makes something like this. It goes lower, and it makes some margin like that, and it is finally it is making something yeah, something like that. It will making changes, so it will how it first it is going, it is lying like this, and it will making it upper and making it upper like that. I have like I have only plotted 10 things. You can first 10 graphs I have plotted. You can go here and change the values, get as many plots you want. I just wrote it to show you like how it makes the model, how it changes, how the line changes as the training progresses like that. You can see here it is making wrong prediction here, and after it is updating its weight like this. After that you can see here how it makes the things like this. After training many times, it can make a prediction like this as SVR, which is predicted using a scalar library. I think everything is clear about this. If you have any doubt up to this, you can ask. Kernel trick is very important in SVM. Like if you have any doubt, you can ask. Yeah, I think everything is fine or not. Yeah, I'm going to like basically we have seen SVM for how SVM predicts. We only see binary classification in SVM, but by using the binary classification technique, we can also use multi-class classification in SVM by using three approaches called one versus one approach, one versus all approaches, and the direct acyclic graph approach. So these are the three approaches we use it to get a multi-class prediction using SVM. Yeah, in one versus one approach, we will create L into L minus 1 into 2 SVMs. Like if there are three SVMs, we will train an SVM to predict only the green and blue class. We will create one SVM like this for predict only the green and red class, and we will create train another SVM just to predict blue and red color, blue and red class things. And if we are giving like this, we will make it to we will train L into L minus 1 into 2 SVMs to give prediction about only two classes. By taking only considering only two classes, we will train one SVM to make predictions. And if we are giving a data point like this, we will see like whether it belongs to if you are giving a data point like this, it will we will see whether it belongs to green or blue passing the data point into all the SVMs. And if three SVMs tells us it is blue and one tells us it is red, we will take it is a blue, because most of the SVM it is telling us blue. Like that, we will what majority of the SVM tells us, we will label the data with that result from majority of the SVMs. That is the main concept here. And in one versus all approach, we will make our SVM to learn to differentiate between green and all other data, and red and all other data, like number one, class one versus all class, which is not equal to class one. We will train our another SVM to predict class 2 versus which all the data points which are other than class 2, like those things. We will train n SVMs for that, and we will pass the data to each SVM, and we will predict the SVM by taking the marginal distance, which like a majority, which SVM tells, like if one SVM tells it is green and it is like that, and if it is green, like other SVM will tell like it is not red, and it other will tell like it is not blue, and like that. So we will make an prediction of the class using that. In one versus all approach, we will train n SVMs. And the main problem with one versus all approach and the one versus one approach is that we need to train many SVMs to get these things, multi-class problems, multi-class classifications. And another thing versus another disadvantage is in one versus all approach is there will be like if there are 10,000 points belongs to 10 classes, each point, let's assume if 1,000 points, each class has 1,000 points. When we are making a classification between one, which are the data points which belongs to class 1, which does not belong to class 1, one class will have 1,000 points and another all will have 9,000 points. So it is unbalanced SVM, so we will get some wrong predictions in that. That is the main disadvantage in one versus all SVM. There are some techniques, statistical techniques to overcome these things, but everything is time expensive. So this is the main disadvantage there. In directed acyclic graph, we will overcome these disadvantages we will which we encountered in one versus all and one versus one SVM. Here we will predict. We will also train L into L minus one, same number of SVMs as one versus one. But the thing is, first we will take, if there are only 4 classes, we will make a prediction between whether it belongs to class 1 versus 4. We will compare whether the point is class 1 versus 4. If an SVM tells it is not class 1, then we will go to we will remove the class 1 here, and we will predict 2 versus 4. We will take the last point, first and last point, 2 versus 4. Depending on if it takes it is not belongs to class 4, we will remove the 4, and we will pass into a SVM which will predict whether it is a class 2 or 3. And after the final prediction, we will get the result. Here, while predicting, we need to pass into only n minus 1 SVMs. If there are 4 classes, we need to pass into only 3 SVMs, like this. Any of the path, only 3 SVMs, so we will get the correct answer. So we need to it will be less SVMs, and the approach is very good, very better than other approaches. Since we are eliminating the classes, it can give the better results. I think everything is clear up to this. If you have any doubt, you can ask. I will go through this in one versus one approach. We will test whether the class belongs to blue or green, or red versus blue, or green versus red. Based on the majority of the predictions, we will send the label. In one versus all approach, that's also like if many things, if one tells it belongs to green, and many other tells it does not belongs to red, or we will reject. If many things rejects other things, we will predict those with Based on that, if some ties there, we will take into marginal distance into consideration. If a point is like this, we will take into the marginal distance. Like it has more marginal distance with the green, but less with the blue. So we'll take a green. It belongs to a green, like this. But the main thing in both is we need to train many SVMs there. But here we will since we are eliminating, it will be good better approach, and we need to train only less pass into less SVMs than other things in directed acyclic approach. So it can give better predictions than other two SVMs. Since computation cost also very lesser than other two. I think everything is clear. If you have any doubt, feel free to ask in SVM. If you have any doubt, you can ask in SVM. Then we can see Neighbours class here. I think everything is clear with SVM. We can go into Neighbours classifier. Neighbours classifier basically works based on the Bayes theorem, which we have studied during 12th, I guess. Everyone is it is conditional probability. It is the P of A bar B means probability of occurring of A given B occurred. This is the basic thing. This is the Bayes theorem which we all know we have studied in 12th. I'm repeating, P of A bar B means probability of occurring of A given B occurred. That is the conditional. That is called conditional probability. Okay, based on this, we will make a model to learn things. We will make a prediction, and we will take a example data set like this. Whether with respect to outlook, temperature, humidity, and windy, we need to predict whether a person will play golf or not. If based on these four features, we need to predict whether he will play golf or not. That is the main thing we are doing here. Here we can see y value can take either 0 or 1, because for yes it will be 0, or for y for false it will take 0, for false it will take 0, and yes it will take 1. Based on the we need to predict whether y will be 1 or 0 based on x has occurred. X is the things which have occurred, like rainy, hot, high, and windy is false, like those things, equal to probability of p of x based on y has occurred. Y is the thing, probability of occurrence of y. X is the thing which has occurred with given y has already occurred, which we know by the data set. This thing is, if y is equal to 1, and if x is equal to, like let's say outlook is rainy, probability of occurrence of rainy with when playing golf is yes. Here you can see, like it is rainy, it is G, but it is no, but it is here rainy, no, but here rainy, yes. So the probability of occurring of rainy is 1 by 3, only 1 by 3 as yeah, it is only 1 by 3 given y becomes yes. That is the probability of rain becoming it is rainy. And that is the thing which this thing we can learn by the data set, and we need to predict this thing by predict probability of whether he will play golf or not, given the future has occurred in the training test data set. X1 take any features like X1 and X2 and X3, Xn, like this. These are the things for future. Here up to only 4. We will take only up to 4. X1, X2, and X3 and X4. By using these things, we will just simply multiply all those things to get the probability of those things. And here we can see we just multiplying these things. We can multiply these probabilities only if we are multiplying these probabilities only if they are not independent of each other. So if they are independent of each other, only if they are independent of each other, like probability of occurring of rainy does not depend on the temperature. We need to consider like that. The day becoming rainy or not, it should not depend on the temperature of the day. We need to consider like these things. These are the conditions we are considering while making predictions with the neighbors. But the main thing drawback with neighbors also, like the most of the in real world cases, they that they will be the features will be dependent on each other, not independent on each other. Most of the features will be like become a day become rainy, obviously depend on the humidity of the day and also the temperature of the day. But these are the things but here we are considering they are independent of each other. This is the main drawback of neighbors. Final how we get the final prediction is, if we are giving a y equal to 1 and we are predicting some probability, we are getting some probability here, let's say 0.6. And for y equal to 0, if we are getting probability like final probability like 0.4, then we will take which has the maximum probability. Like here, let's say if y equal to 1, we are getting 0.6, then we will take it is 0.6. This is the highest probability, so he will play golf there. That is the main thing. Let's see if there are some continuous variables comes like this, like the salary of the person is given, and we need to predict whether he will play, if he will buy a book or not, like those things. If the here is there are no continuous variables, but if continuous variables are given, we will take some probability density functions, like normal distribution. That is, it is why it is called Gaussian. Gaussian distribution is the normal distribution. It's has a formula for like this formula probability density function of like this. It will give the probability given the continuous for the continuous variable x of I. It will give the probability, and mu of y is the mean of the x that column of data, and sigma is the standard deviation of the column of like, if there are very salary of 10% is given, we will take the mean of the data and put it here, and we will take the standard deviation of the data and we will put it here, given he has bought. Like if the 10% salary is given and he all of the like 5% have bought the data or bought some laptop like that, we will take only the 5% salary and we will calculate the mean and put it here for a y equal to s, and take the 5% salary standard deviation and we will put it here, and we will calculate the probability density probability by using this function. That is how we can get a probability for continuous variables. We can use other functions like Bernoulli, like those functions. But the Gaussian works fine in many things. In conclusion, like Neighbours is very simple and easy. It is very less costlier than costlier means it is quicker than other KNN and SVM. But it can be used in many things like spam filtering, recommendation systems. Like basically, like we can use this in which the variables don't depend on each other. Which is independent on is like if the features not dependent on each other, we can use this VM. But not SVM like Neighbours, but in many real world cases, like they are dependent on each other, so we cannot use Neighbours. That is the main drawback of Neighbours. And here in Iris dataset, we have put the Iris dataset. I'm taking the first four features and the species value as the target. And I'm same thing. I'm supplying here, and I'm taking the 0.2 as the test set, and 0.80% as the training. And I'm same thing. I'm doing the standard scalar function here, and the fit transform thing here, and I'm getting the Gaussian NP function which I imported in the using the sklearn library, and I'm training the model, and I'm predicting, and I'm for accuracy it is getting 100% accuracy, because like the same thing. Iris dataset is a very simple dataset. It has like, it is easy to visualize. It is grouped together, so it is giving 100. But in most of the cases, SVM is better than other two, KNN and NEBs. That is the main thing. Do you have any doubt in Neighbours? If you have any doubt, you can ask. If you guys having any doubt in Neighbours, you can ask. I think everything is clear for you, I guess. I am assuming that. I think I'm not boring you.
Okay, I guess we can move on. So thanks,
Okay,
Sudan. Maybe
next.
Sudan, you can start presenting, and we'll start.
Yeah, my Sudan
Maybe
will
before that,
stop.
yeah. Do you want to take small break? Maybe we'll start at 3:45.
Yeah, that is also nice.
So yeah, so basically, what we had discussed till now, we discussed three different machine learning models. So naive Bayes is basically like the simplest model that we could use using probabilistic methods, SVMs and KNNs. So we'll be discussing some more methods the next class. So all these are independent models. They don't need like previous knowledge of one to like understand the other. So, but how do we compare these models, right? So we need like to we need a metric to compare. So you had seen one it's very simple metric called accuracy, which just says whether it is equal to this or not, right? So that is one of the methods, and we also have like several other accuracy metrics like F1 score, precision recall, which we'll be going ahead, which we'll be like discussing about all those right now. So once we start at 3:45, you can like we'll go through like some other classification metrics, and I think that will be the end of this session. Okay. So we'll start again at 3:45.
Can we start?
Yeah, Sudan.
Yeah. So I am Sudan. I will explain about common performance metrics in machine learning. So like performance metrics are in any machine learning pipeline you will find a performance metric at the end to analyze how the metric how the model is performing. So based on the true values and the predicted values, it will check if your model is making progress, and it will put a number on it. Like uh, many times what you will do is you will have a dilemma on which value of parameter to use while training the model. So at that time what you can do is you can compare the value of performance metrics and choose the value of the parameter which best suits the performance metric. Usually in Kaggle competitions, we can find that the final leaderboard is based on a performance metric like accuracy or precision or recall. So performance metrics are usually divided into classification metrics and regression metrics. So classification metrics are used for classification problems, and regression is metrics are used for regression problems. So starting off with regression metrics, uh, only two main regression metrics are present, which are already discussed in the previous session, which is mean squared error and mean absolute error. In this session, we will focus mainly on classification metrics. So let's start off with classification metrics. There are four main classification metrics: classification accuracy, precision, recall, and phone score. So we will go through about all of this and explain. And before that, we will start off with confusion matrix, which is a prerequisite for understanding about classification metric problems. So uh, confusion matrix is basically a array or basically a table, which is a tabular visualization of model predictions and truth labels. So each row will represent whether the each row will represent the actual value of the class, and each column will represent the predicted class. So here you can see that first row contains classifications, data points which are positive in actual class, and second row contains data points which are negative in actual class. In the column side, you will see that there are two columns. First column tells whether the predicted prediction says it as positive or positive. Second row tells whether it is whether the prediction is negative second row uh, tells that the prediction is negative. So uh, here if the classification is binary, usually it will have only four classifications, like true positive, false positive, and true negative. If there are n categories for classification, the confusion matrix will be n cross n. So like uh, let's dive deep into each of these categories: true positive, false positive, and true negative now. So before starting to understand about this, we need to have a null hypothesis, or a value or a statement which is which, if it satisfies, it is considered as true statement. uh, so suppose we are going to the doctor and for a cancer, checking whether we have cancer or not. So first starting off, we'll think that the null hypothesis is the individual has cancer. If we have cancer, we will fall into positive case. If we don't have cancer, we will fall into negative case. So as we can see, actual condition will be on rows, and predicted condition will be on columns. Actual condition is whether whether you really have cancer or not. Predicted condition will be whether the prediction tells that you have cancer or not. So each cell in the confusion matrix will tell the number of true positive or true negative or false positive or false negative. So true positive signifies the number of positive class samples that we have predicted correctly. Suppose there are suppose you have cancer and the predictor also says that you have cancer, then this data point will fall under true positive. Suppose the individual doesn't have cancer and the predictor also predicts that the individual doesn't have cancer, it will fall under true negative case. Next comes false positive. Suppose uh, suppose the predictor predicts that you have cancer, but actually you don't have cancer, it will fall under false positive. This error is considered as type 1 error. And we will talk about this more about in recall metric. And the fourth and final is false negative. It signifies how many positive class samples your model has predicted incorrectly. Basically, if the individual doesn't has cancer, but the predictor or the doctor predicts that he doesn't have he doesn't have cancer, it will fall under false negative case. So the individual has cancer, but the doctor has predicted that he doesn't have cancer. So these four are the main parts of confusion matrix. So uh, in sklearn we have a function which is used to generate confusion matrix. If we give it the true values of y and the predicted values of y, it will generate a confusion matrix array. So I have just taken two data sets. It doesn't have any meaning. It doesn't have. It is not from Iris. Just two data sets to make people understand how this works. So confusion. So this example confusion matrix, I have fed that y true example and y predicted example, and I have used plot confusion matrix example function from sklearn.mlextend.plotting to plot the confusion matrix. I have fed in the confusion matrix array inside it, and I have given the figure size and other specifications. So automatically it will predict, it will print the confusion matrix. So as you can see, uh, uh, and the left hand side contains actual values and the columns contains predictor values. So now we can see that there are the dark green color shows the true positive and true like the model has actually predicted correctly the diagonal values. Like there are two zeros and the model also has predicted that there are corresponding value is 0, and at the end we can see that there are two ones, and the model has also predicted that there are two ones. And the light green color basically represents the error in the data set. Does anybody have any doubt, please? I heard someone talk. Okay, so I'll continue. So the diagonals actually represent that the model has predicted correctly. If the number of values in the diagonals are maximum, it will say that the model has predicted correctly. But non-diagonal values, if there is any number present, it actually says that there is error in the prediction. So using this confusion matrix, I have using the confusion matrix function, I have plotted the confusion matrix of SVM model predictions, Naive-Bayes model predictions, and KNN model predictions. As you can see, I have generated the confusion matrix arrays from these y test y pred and y test y pred of Naive-Bayes and other KNN values also. So coming to SVM, while training SVM model, we had only considered 2 flowers. We had dropped a third flower to make it simple. We had only considered setosa and versicolor. That's why the confusion matrix is 2 cross 2. Now, if we had considered the third flower also, the confusion matrix would have been 3 cross 3. As we can see, we have fed 4 setosa, and the model has also predicted 4 setosa. That's why the top right has 4, and it says that all 4 data points are predicted correctly. And on the bottom right, we can see that for versicolor, basically entry 1, we can see that all 6 entries are predicted correctly. All 6 versicolor flowers are predicted as versicolor. So, and at the left bottom and top right, we can see that the values are 0. So there is no cross prediction. So basically, the model has not has no error, and it will have an accuracy score of 100%. So in the same way, I have predicted I have plotted the confusion matrix for Naive-Bayes. Here we can see that we have actually fed with 30 data points, and we can see that since we have while training a Naive-Bayes model, we had three features for classification. That's why we have 3 cross 3 matrix. Here actuals are here 0 represents setosa, 1 represents versicolor, and 2 represents virginica. And we can see that all setosa plants are correctly identified as setosa. All versicolor, all virginica plants are identified as virginica. But only one data point is wrongly predicted, which is a virginica plant is identified wrongly predicted as versicolor. That's why we have at this entry 1. Basically, if it is a 100% accurate model, it should here instead of 7, it should be here instead of 8, it should be 9. But since there is a minor error, we have a non-zero value at the non-diagonal value of the confusion matrix. It is a minor error, so it's acceptable. At the same time, we have I have plotted the confusion matrix for KNN model. So we can find that there is very less difference between KNN model predictions and Naive-Bayes model predictions, but there is only one minute error. The two we can see that there is a value of 2 instead of 0 in a non-diagonal entry. This basically means that two virginica plants are identified as versicolor plants. So we can see that this is quite less accurate than Naive-Bayes model. Other than that, all other flowers are predicted correctly. So compared to all 3 models, KNN model has performed the worst. If anybody has any doubt regarding confusion matrix, please speak out. assuming nobody has any doubts, let's move on with classification accuracy. So classification accuracy is basically total number of correct predictions divided by the total number of data points in the data set. So how many positive values we have predicted as positive and how many negative values we have predicted as negative divided by the total number of points. So that's why for classification accuracy we have in the numerator we have true positive and true negative, and we have summed them up, and in the denominator we have total number of predictions. For this is the one of the most important metric for ML models. So we have an inbuilt function from sklearn.metrics which is accuracy score to find accuracy score of any prediction. Like if I feed y test and y pred, it will automatically give the accuracy score. So I have printed the accuracy scores of SVM model, Neighbours model, and KNN model. So accuracy score of SVM is 1. Since from the confusion matrix we had seen that only central diagonal elements are filled, and in the Neighbours model we have accuracy score of 0.966, which is close to 1, and it's fine. The reason it is not exactly 1 is because we had a single wrong prediction, and as we had seen from the confusion matrix, the accuracy score of KNN model is 0.933, which is due to the reason being we had 2 wrong predictions. You can also see that the 1 minus accuracy score here, 1 minus accuracy score for Neighbours model is 0.33. 1 minus accuracy score of KNN model is 0.66, which is double of Neighbours models. It is because we had 2 wrong predictions in KNN model, and we had only 1 wrong prediction in Neighbours model. The accuracy score of SVM model is 1 since everything is predicted correctly. So if anybody have any doubt regarding classification accuracy, please ask in chat. Okay, assuming everybody understood about classification accuracy, let's move on to precision. Precision also it is somewhat similar to classification accuracy. Just we are reducing the denominator to only positive class variables. So what precision does is it checks how many of the positive class we predicted is actually correct. Suppose we are going to doctor. Suppose we are going to doctor, and the doctor has predicted as non-cancerous. Even suppose the doctor has predicted as cancerous, even though we are non-cancerous. So that will fall under false positive case, and it is of type 1 error. So what precision does is it divides true positive by true positive plus false positive. From the confusion matrix, we can see that true positive is all positive cases which are also predicted as positive. False positive is positive classes, negative classes which are predicted as positive. That's why it's there is a suffix prefix false. So precision actually checks how many positive predictions are actually correct. So it focuses on type 1 error. If we have a high prediction value, it automatically means that we have a low type 1 error. So suppose a real life example of precision is suppose a court hearing is happening for a suspect, and if he is actually innocent, but the judge actually deems him guilty, and in that case he will fall under false positive category, and type 1 error will increase, and precision will reduce. So to implement precision score, we usually use uh, a inbuilt function from SQL and dot matrix, which is precision score. So if we input y test and y pred, it will automatically output an array or a singular value based on the dimensions of the y test. And so in the SVM model, we had only considered two flowers.
Not yours. Yeah, very good.
Okay, I think his like battery has died. So just give us like 2 minutes, we'll come back. Okay, I think there is a small technical issue from his side. So you just let me present. So I'll continue on his behalf. So basically, can you see my screen? Please, Surya question. Is my notebook visible?
Yes.
Yes, sir. Okay, so great. So basically, we'll just like start from precision again. So when you predict like a model, right? So let's say you have two classes, class 0 and class 1, and you want to predict the object whether it belongs to class 0 or class 1. So when you predict it correctly, let's say you have an apple and a potato, and the classes are fruits and vegetables, right? So if you predict apple as a fruit, then that is called a true positive. And if you predict potato as a vegetable, that is also true positive. But then when you predict potato as an apple, that is called basically a false positive. Okay. So it is not true, but then you predicted it to be an apple. So basically precision is given by true positive by true positive plus false positive. So what this says is basically the the probability that, not probability, like the fraction of your predictions which has been predicted to be belonging to this class by the actual class count by the prediction of objects which have been predicted to this class. I hope it is fine, right? So basically, if you like take this example, like cancerous patients which have cancer, that is the actual ground truth. So out of the actual data set, these many people have cancer. But then your model predicts that some more people are also having cancer. So that is basically your false positive. So precision is basically the actual number of people who have cancer by the total number of people who which your model predicts to have cancer. So that is basically your precision. And recall is actually very simple, very similar. It is basically the opposite. You actually have some people who have cancer, but then you're like trying to find out how well your model actually performs on that particular metric. So let's say you have people who have cancer, and then you let's say your model predicts that they don't have cancer. That is necessarily a bad thing, right? So basically, you don't want that to happen because that actually will hurt your model than predicting whether people have cancer or not. So your recall is nothing but the people who actually have cancer by who you predict you think have cancer plus who you predict who don't have cancer but actually have cancer. So that is basically a recall metric. So again, SKL1 as a recall score, which actually does this for you. You can actually use the normal recall score to predict that, and also you can use your you can also like do it by your own. So you just have to find out how many people have cancer and look at the predictions which your model predicted that doesn't have cancer. I hope that makes sense, right? So is it fine? Maybe you could like just use some reactions to tell me whether you understood that. Okay, so I guess you didn't understand. So maybe let's look at it again. So you have two different outcomes. You either belong to that class or you don't belong to that class. So in reality, you have two options: belonging to that class and not belonging to that class. And your model is also predicting whether you belong to that class or you don't belong to that class. Let's call it, in reality, it is A and B. Your model, if it predicts, it is 1 and 2. Okay. So if in reality you belong to that class A, and and your model predicts that your object belongs to the class 1. So A1, so basically A and 1, that is called a true positive. If in reality it doesn't belong to the class, that is B, and your model predicts that it belongs to the class, so that is B1. B1 is nothing but a false positive. And similarly, in reality, if it belongs to the class B and you predict that it belongs to the class B, so it is B2, that is again true positive. And in reality, if it is B and your model predicts that it doesn't belong to B, that is B1, then that is like false negative, right? Because it actually have to belong to class B. So you have all these combinations. So you have two combinations in reality and two more combinations that your model predicts. So which in total is four combinations: the true positive, false positive, true negative, and false negative. So basically, these four values you can just find out by going through your actual ground truth values and your predicted values. And you just find the number of true positives and you find the number of false negatives. You take this sum, true positive by true positive plus false negative, that is basically your recall. So this actually tells how well your model predicts for those people who actually have the cancer. So this having a very high recall is more important than having very high accuracy. So this actually tells you whether your test is useful or not. So let's say you have a COVID test and your recall of that COVID test is very low. Let's say it is 0.8, but then your accuracy is very high, 0.95. So since your recall is low, the test doesn't actually say whether you actually have COVID or not. So it is very important to have a very good recall score than a very good accuracy score. I hope that makes sense, right? So F1 score is basically your combination of these two, your recall and your precision. So this actually tells how your model predicts for a person who does not belong to the class, but and then a person who belongs to the class also. So also again, having a good F1 score is better than having a good accuracy score. So again, yeah.
Ajit, there was one question from Srinivas. Yes, how do we tell what is false positive or negative in case of things having more than just true or false?
So all these metrics, right? So F1 score, precision, recall are used for binary class classification. So you only have two classes, class A, class B. So if you want to have for more classes, what rather you would do is you would you do it for every class. So you like, let's say you have four classes, you will compute F1 score for that particular class. You would compute F1 score for the second particular class, and so on. Does that make sense? So for every class, you will have a different F1 score. Right. Okay, Srivas. Okay, good. So now we'll just move on. So basically, you have one more thing that is called ROC curve, and there are like some 2-3 full forms of this. We'll just go with receiver operating characteristic curve. So here, what again you do the same thing. Okay, you find out what is a true positivity rate. So that is your recall, and one more thing, you find out your false positive rate. So you find out false positive rate and your true positive rate, and you basically like have a threshold. So let's say basically if you have some value which is more than 0.5, and you take all those values. If it is less than 0.5, you chuck them. They are not significant enough. So basically, if you just look at the data set that you have here, so you find out the true positivity rate, that is the recall, and you find out the false positivity rate and your prediction probability. Okay, and you apply a threshold on it. So once you apply a threshold on it, you have basically you have two curves. Basically, you find out this. You like use a random classifier, which is basically 0 or 1, which is always going to give you a 50% accuracy, and you have your like better curves. So if you see your green curve that is here, maybe I'll zoom a little bit. So if you see your green curve, if you see that is slightly better than your random possibility, your orange is better than that, your blue is even better than that, so on. And your perfect classifier is going to be just one single point. So it's not a function, it's just a discrete point. So yeah, so again, you let's say you want to so here you can see here, right? So mean is basically nothing but your random guessing, which is as good as 0.5. And you if you have a ROC curve, basically here it is a singular point, so it is going to be just two asymptotes at x equal to 0 and at y equal to 1. So that is your ROC curve for this. So if you have multiple predictions, right? So then you have something like this. This will be something like an asymptote, but your mean is going to predict somewhere in between. So for like your positivity rate equal to 0.4, 0.6, your mean does worse. But for anything more than that, your mean is slightly better than that. So yeah. So these are all different metrics which give you like a sense of how well your model is working with respect to one particular like behavior of the model. So you can see that your recall is probably like trying to give more importance to the people who actually belong to the class. Your precision is going to give you like importance to the people who actually doesn't belong to the class, but your model like tends to think that it belongs to the class. Your F1 score is going to be some like combination of these two. So like it depends on what the use case is. So for a simple multi-class classification, right? So it might not be feasible to compute F1 score for all the possible classes. Does anyone make sense? You don't have one. You cannot compare one F1 score with another F1 score. Right? They don't belong to the same distribution. So then a normal accuracy metric is probably good enough. But then when you have just two binary classes and you have lot, so like this usually helps in case of very skewed data sets. Even though you have like lot of data points, let's say that let's say you have 100,000 data points, but then only 1,000 people belong to the class that you want to worry about. So that is only out of 100,000 people, just 1,000 people have cancer. And a normal linear regression model or a logistic regression model, if you want to try to like predict, right? So linear regression to predict how probable that you have cancer, logistic regression to just say whether you have cancer or not. So basically if you want to like train these models and you like just say that you don't have cancer, right? So that is going to give you a 99.99 accuracy. Like that doesn't necessarily quantify how well your model performs. So in that real life situations where you want to alleviate your like class imbalance, you want to get rid of the class imbalance, you use other predicts like accuracy like recall score or F1 score and so on, right? So I hope that makes sense. And when you have multiple classes, probably weighted accuracy score is a better metric than finding F1 score for particular classes. Okay, so I hope that makes sense. Right. Maybe give me a thumbs up or something on the reaction so that I know you are following. Okay, so I have one. So maybe this session is slightly more difficult than the previous sessions that we had conducted because this actually is a very discrete methodization of classifying data points, right? So you don't have any logic behind an SVM. So someone had come up with that method, and it makes sense to discuss about that. So we had discussed. So there is not a lot of logic behind why one would choose an SVM over a simple KNN or so on, right? So it all depends on how well you want to characteristic your model. So if you want to if you want a really good prediction, you might prefer an SVM even though it is more cost. So so these are all just different options for you to explore, and just looking at different options doesn't necessarily make sense. So we'll discuss about how it works, and then we proceeded. So from next class onwards, I think there will be a little bit more structure to the sessions, because I think next class we'll be discussing a little more about I think two more machine learning models. After that, we'll be discussing recommendation systems, and after that, I think once we start into deep learning, right, you will find the connectivity between why machine learning models are slightly old and why deep learning models are preferred right now. So once you maybe move past this 2-3 sessions, right, you'll understand why we discuss these, and you'll appreciate the content for that. I hope that makes sense. So just stick around with us. So if you didn't follow something, feel free to put it on the group. We are there to help you out, and also you can look at the recordings. We'll be posting it soon. So just go through it. If you want some articles where you can learn about all these, also let us know. We'll provide that. So I think yeah, so basically that's all we wanted to say, and I guess that's the end of today's session also. So yeah, so I guess do you want to say something, Surya?
No, bro, but SVM is a very good model. Like it has many details. It is used in many. It can make good predictions than KNN and Neighbours in many cases. But it also costly. That is the thing I want to add. Yeah, that's
Yeah.
it. And
Okay,
even if you
so
didn't
just
understand,
yeah,
even
go
if
ahead.
you didn't understand, I will send a video which I used to take a video by MIT professor who took very well, and you can see his video with Kane and sorry SVM. He went into deep. It is very good. Yeah, that's it.
So we'll share all those resources, and just to let you guys know, we'll be having another session on continuation of this, not necessarily dependent on whatever we had today. So the next session will be on Wednesday at 2 p.m. again. So stay tuned. I guess we'll end today's session then.